Yeah, good evening, it's Charlie ZL2CTM. Well, I'm about to disappear on another business trip, and I thought I'd just do an update video before disappearing, sort of talking about what I've been playing around with over the last week. Since the last video, I've decided to build an AM transmitter receiver, and based on a bit of a steer from Paul, thank you very much, I'm going to look at a pulse width modulator based AM transmitter. So that was certainly some useful tips there from Paul, and another good article I found online from a Stephen Cloutier, I think it is, WA1QIX, also had a very good sort of rundown on some of the work that he's been doing over many years with AM pulse width modulator transmitters. So I'll talk about the circuit in a sec. So what do I mean by a pulse width modulator transmitter? So what I'm going to try and build is this, in terms of a simplistic block diagram here. If we just sort of look down the bottom right hand corner here, our RF amplifier, I'm going to play around with either a class D or a class E for something different. Because of the high efficiency and the less amount of heat that this is going to generate, which will make heatsink a little bit easier. I'm going to look at around, if I can, roughly around sort of 10 watts on an output. We'll just see depending on what I can find available for an overall VCC. But that's sort of what I'm looking at, and using pulse width modulation to get our audio onto that carrier. So amplitude modulation, as we know, this particular method here is the VCC line that's going to the RF amplifier. That DC there is going to vary, and it's going to vary at the audio rate from our microphone. And by doing that, our output carrier is then going to be amplitude modulated, where we get our AM from. Rather than using a big bulky modulating transformer to impress onto that DC current coming through here, our amplitude modulation, I'm going to use this pulse width modulator approach. Less heat, less bulk, and really been quite interesting from an academic point of view, trying to get this to work and sort of thinking about how it does work. So sort of moving back around, I guess, the way this works, at this point here we have this pulse modulator is essentially a switch, and it's switching on, off, on, off, on, off our VCC, and the rate in which that's been turned on and off is a function of this pulse stream that's coming out. The pulse width, in other words pulse width from our modulation, the width of those pulses is a function of the audio frequency. So the audio frequency goes through here, and we'll talk about this in a sec, produces this stream of pulses, the width of which is proportional to the audio. It turns the switch on and off, and out of that switch we get essentially 0 to VCC, looking like that, but between 0 and VCC. Now we need to get rid of all those high frequency components from the square wave before we amplitude modulate it or feed it to our RF amplifier, so we don't transmit any out of band signals, and we do that by using a low pass filter here. Now, so in order to generate that stream of pulses of varying width, we use a comparator, and the input to that comparator is our audio, which you just mentioned before, and the other side is a triangular waveform. Now that waveform there doesn't have to be uniform in terms of the time it takes to rise and fall don't need to be the same. It just needs to be periodic, and more importantly, the sides need to be nice and straight. Now, reading through some of the literature, and Stephen, like I say, had a good write-up on this. In terms of trying to select a frequency for this waveform down here, it turns out that, oh well, I understand more the point, that the AM radio stations typically use a frequency between 50 and 100 kilohertz. So I elected to use 70 kilohertz to be sort of roughly in the middle of that. So that's what I'm using, 70 kilohertz. Right, so I think that's probably enough in terms of talking about the overarching block diagram and where I'm trying to go. So now just talking about this portion here. I tried to make these two components here, the triangular wave generator and the comparator, out of commonly available operational amplifiers. So I initially tried using an LM324. Configuration here is certainly not my design here. No, this you'll see this many times on the internet. So you've got a Schmidt trigger here combined with an integrator to basically generate as an output a triangular waveform. And I won't talk about the comparator at this stage of the game. I made the circuit up and got the frequency worked out quite nicely. So the formula there for working out using those values what the frequency will be. And while I managed to produce an output waveform, it really wasn't clean enough to be used. It didn't have nice straight sides. It was sort of a little bit jagged. Well, not jagged. It had some artifacts in there which I just really couldn't get out. And I put that down to ultimately that the LM324 is not really a high-speed device, and the slew rate just really wasn't going to be high enough for 70 kilohertz. If I dropped that frequency down to a couple of kilohertz, it got extremely good. It was fine, but up at 70 kilohertz, it just really wasn't. It wasn't cutting the mustard. So, in the end, what I decided to do, I elected to try a little chip that I haven't used before, an AD9833, and that's what we see over the back. So that there is just a couple of dollars here in New Zealand. It's quite a common device. It's used, or it can produce, more to the point, triangular, sine wave and square waves. Very simple communications protocol with a microcontroller. And look at the output in a sec. I'm using a little Arduino Nano there to drive it. The radio is going to have the Nano in it anyway, because certainly from a receiver point of view, and also the VFO for the transmitter will come from, I haven't got there yet, either a 9850 or an SI 5351. So I'm going to need that microcontroller there for that anyway. So well, might as well just then include this little triangular wave generator. The waveform that produces is a lovely waveform there, as we can see. That's at 70 kilohertz, and certainly nice and clean, nice sharp points, nice straight sides, and works very, very well. So, and like I say, for a princely sum of just a couple of dollars, it was an easy way and a good way to produce that triangular waveform to feed into the comparator. Now the comparator itself, like I initially tried the LM324 standard op amp, and really, like I say, at the 70 kilohertz just wasn't going to cut the mustard. So I elected to use an LM318N, which is what we see down here. That device there is just $1.50 here. Has a much faster slew rate and works well. So there's two inputs there, and what I might do now is just quickly look at how it's configured. So ignoring this device here, but just looking at here, we have that LM318N is set up as a comparator. For the non-inverting input, I've got a virtual earth set up here. So between 12 volts, our VCC and ground, I've got two 10 k ohm resistors with a couple of 10 microfarad capacitors in parallel to set that up at half VCC. The audio frequency input is currently coming in from a SIGGEN, and I'll talk about at the end the audio amp for that, through a 1 microfarad ceramic capacitor, so at 105 there. The inverting input I've got coming from a little 10k pot there, which just allows me to vary the triangular waveform coming in to ultimately set how wide those pulses start, which ultimately will set then the modulation depth down here. Right, so where am I going with this? Right, and the output of that. Okay, that's fine. So let's have a look at the output of that, and then we'll go further and talk about the rest of the circuit. Let me just switch to there. Let me just transfer across to the output of that comparator. And let me just leave that. So that's the output of the comparator. And I've currently got the audio frequency coming in set to be 2 Hertz. I set it at a really low frequency just so we could see that pulse width varying at the audio rate. And like I said, by adjusting that little potentiometer on the inverting input, I can then set what the default width is, which will ultimately set what that DC, the quiescent DC current will be feeding through to the power amplifier. So that's the output of that. Just going back to here. So just back to our block diagram. So what we just saw there was this this pulse stream coming out of our comparator, the width of which varying at our audio rate. And now just looking at this pulse modulator here, that's a MOSFET, and that's the configuration there that I've used. That MOSFET is being driven by a MOSFET driver. It's just a small device, just $1.40 here in New Zealand. It's an MC34151P. This seems to be quite a common driver to use, or it's quite common to use MOSFET drivers because they handle that high input capacitance of the MOSFET. And at that price point, I thought, well, why not try and make this as clean as possible. The output of that is very much just a repeat of this, which is then driving that MOSFET. The MOSFET I settled on was the RF640. I did try a number of other ones in there, 510, 520, 540, and the like. They all work just fine in this test configuration. The reason why I settled on the RF640 over and above, say, the 510, for a few reasons. The 640 can handle 18 amps through it, as opposed to 5.6 with the 510. It can handle 200 volts across it as opposed to 100 volts for the 510, and its on resistance is 0.18 ohms as opposed to 0.54 ohms, so the voltage drop is less, so less heat. So that's what I've settled on that. It is $3, so not a huge amount of money, but it seems to work just fine. Now we mentioned too, if we just were to cut back to the block diagram, that's essentially a switch, on-off switch, switching our VCC through ultimately to our RF power amplifier, and we need to clean it up first with this low pass filter. What I elected to use in the end, I'll sort of hold on a bit of an angle here, was a Butterworth 4th order filter. I used a piece of free software online called ELSIE, E-L-S-I-E, which works really well for determining, in this particular case, a Butterworth 4th order low pass filter. Now, so in terms of what the parameters were for setting up that filter, by all accounts from reading the literature, the cutoff frequency for that filter needs to be somewhere between 10 and 12 kilohertz. I elected to use 10 kilohertz, and for the termination impedances, I'm going to use a bit of a steer from Stephen's paper, where he's assuming somewhere between 6 and 8 ohms, when I use 6 ohms. So the 6 ohms is the terminating impedance for the design work of that particular filter. And that's what it produces. It produced 2 inductors, one 36 microhenries, the second one 88 microhenries, 2 capacitors, and I've just gone for the nearest standard value, so 4.7 microfarads and 2 microfarads. And that's what we see down here. Now I was quite lucky. It seems to be quite common to use a T106-26 core for these. For the high or sort of the higher power transmitters, you do need to provide quite a bit of current. So that's why we've got the big core here and the heavy gauge wire there. I was quite lucky some time ago to buy some surplus chokes. I'm not quite sure where I got them from. There's a whole bag of them, but it just turned out that they were actually T106-26 cores, pre-wound in some cases with 50 odd turns of quite a heavy gauge. So that was quite fortuitous. So it's just a matter of unwinding that and stretching the windings out to get the desired inductance. Those two are sitting at right angles to each other just to reduce the mutual inductance between the two. And like I say, those two high voltage capacitors. Yes, high voltage for my circuit, and I think and certainly for the 10 watt transmitter, were a bit of an overkill, but you know, I had them available, so it was certainly nice and easy to use. Right, so what I will do is just have a quick look at, back on the scope, the output of that low pass filter. So if we were to go back to our other channel, that varying waveform you can see there is the output of that low pass filter. If I was to remove the earth that's been provided to that particular little board there, the filter is no longer filtering, and as you can see there, that's what we would be, well, that's the input essentially. That is the input to the low pass filter, and that would be being fed then through to the RF power amplifier, which would not be good. Put the earth back on again, and as you can see, it just cleans it up really nicely, which is good. The only other thing I neglected to mention, there is a, it's not drawn here, there is a high-speed diode that runs from the output, in other words the output's on this side here, of that MOSFET through to ground, and that's what we see over here. So in the off situation, when the flux is collapsing in the coils, that back EMF is being shunted to earth through that. Rightio, so what else did I want to cover? Right, so I guess just to finish off, in terms of next steps, that seems to be working well. You can't quite see it very much, but that little light there is varying at the audio rate at 2 Hertz, and then if I was to quietly change that that potentiometer, you can see I can vary the its quiescent level. Right, so in terms of the audio amplifier, it's pretty important that that audio there is filtered, and we want the filter, or the highest frequency coming in there, to be a whole lot less, way less than our what we call the switching frequency here, or that triangular waveform there. So what I'm going to do for that, I'm going to use another op amp. I'm going to use the 5534, a little low noise op amp, and I'm going to have it set up as to also include on the input here that an RC low pass filter. So a low pass filter configured op amp. Our gain will be, in this particular configuration, 1 plus R1 over R2, as we see there. I think for experimenting, I'll make that a 10K trim pot, so I can vary that DC voltage being fed back, which will ultimately vary the voltage gain of this op amp, which gives me then just another way of varying the inputs to that comparator there for experimenting. Excuse me. In terms of the cutoff frequency for that low pass filter, it's a second order, so FC, our cutoff frequency, our minus 3 dB point for that, is 1 over 2 pi R3R4 times C1 C2. So R3R4 C1 and C2. We can make life a little bit easier for ourselves if we make R3 equal R4 and C1 equals C2, and then that cutoff frequency, the formula collapses down to 1 over 2 pi RC. In order to minimize some of the losses on the input, I'm just going to notionally make our resistor 10 ohms, and in order to keep that higher level frequency of the audio well away from that triangular waveform frequency of 70 kilohertz, I'll use a cutoff frequency of 15 kilohertz, which will be ample for amplitude modulation. So just now rearranging that formula to make our capacitance the subject, we can then solve to find out what that is. So 1 over 2 pi times 100 ohms times our cutoff frequency of 15 kilohertz comes out of 106 nanofarads. So we use the nearest standard value of 100 nanofarads. So that's going to be the next step, is to build that and then feed that into that comparator, as opposed to using the signal generator that's being used at the moment. After that, it'll then be a matter of having a play around with what will be this RF amplifier here. Like I mentioned before, the oscillator here will be probably a 9850 or an SI5351, we'll have to see, being controlled by that nano. And like I say, we'll start to have a play around with this amplifier here. Do want to play around with Class D or E, just for the high efficiency and the like. So that'll be the next step, and then hopefully get a transmitter up and running, and then start to downtrack, slowly work on the receiver. Okay, well, I'm going to call it quits there. I've rambled on way longer. Like I say, and I'm going to say it again, I've said it many times before, I'm absolutely in no way, shape or form an expert in this. This is purely me just playing around and experimenting. There will be no doubt several points in the video where I've made an error or said something incorrectly. I apologize for that. These are not tutorials. This is purely just me playing around with, in this particular case, a pulse width modulator, for an AM transmitter. Okay, that's enough. I'll say 73s. Cheers all, and I'll catch you once I get back. Cheers.